Earth's climate has been changing for billions of years. Sometimes it's been hotter than it is now, and sometimes it's been colder. Sometimes there's been more carbon or oxygen in the Earth's atmosphere, and sometimes less. But something really strange has been happening over the past century. There has been an unprecedented skyrocketing in the temperature of the Earth. We're talking more than a degree Celsius warming in less than 100 years. This is unheard of in the entire geologic history of our planet. For decades, scientists debated the cause of this warming. In the late 1980s, scientists finally realized and discovered what was causing this unprecedented warming. It's the release of greenhouse gases like carbon dioxide and methane from human activities. Over 97% of climate scientists agree that it is human activities that are causing this unprecedented warming. So the debate isn't whether this is happening or not, or whether we are responsible for it or not. The debate is how bad is it going to get, and what do we do about it? There are two sets of problems here when it comes to climate change. One is the fact that the Earth is getting warmer. And with more heat in our atmosphere, there's more energy. And with more energy, there's more opportunities for extreme weather events. And the other thing is that our climate is changing. And we've built our civilization assuming that sea levels will remain the same year after year, or that rivers will flow consistently, or that we can irrigate crops consistently again and again, depending on rainfall. But with change, it's all up in the air. With extreme weather events, places might dry out or experience horrible floodings. We depend on consistency in order to feed ourselves and to live and to thrive. And the change that we are causing can disrupt all of that. All the evidence we have accumulated around the globe for decades point to a warming world. And it's all consistent with each other. So for example, we have rising temperatures, but not just on the land, but also in the atmosphere and on the oceans and even in the deep ocean. Everything is getting warmer, but it's not getting warmer in the uppermost layers of the atmosphere. This is telling us that whatever is driving climate change is not coming from outside the Earth, like increased solar insolation, because that would mean all layers of the atmosphere would get warmer together. Instead, it's happening near the surface. We're also measuring more carbon dioxide in our atmosphere, which is exactly what we expect if it's correlated with increased greenhouse emissions and a warming world. We're also seeing more acids in the ocean. Carbon dioxide in our atmosphere can get pulled into the ocean waters and circulated deep down. And we're seeing a rise in the acidification level of our oceans consistent with more carbon dioxide in our atmosphere. We're seeing a measurable, statistically measurable increase in severe weather events. We're talking more hurricanes on average, more droughts and fires on average. Year after year, even though there can be little variations from year to year, when we chart this over the course of years to decades, we see a statistically significant increase, which is what we expect with a warmer world because there's more energy available to drive these extreme events. Along with that, we're seeing more broken records, more of the hottest days ever, or hottest years ever, or warmest winters ever. We're seeing it again and again across the globe. We're seeing an increased rise in sea levels, a measurable, statistically significant rise in sea levels. That's because the oceans themselves are getting warmer and they're hotter, and hotter things take up more volume. Our oceans are getting physically larger, and that is rising the sea levels. Along with that, we're seeing a consistent loss in Arctic ice. The poles are suffering the most from this climate change, and we are seeing glaciers retreat measurably. We are seeing Arctic ice sheets retreat year after year measurably. It is all here, and it all points to the same conclusion: a warmer world. Let's take a look at a highly simplified model of the Earth's climate. Now, I know the Earth's climate is much more complex than what I'm about to show you, but don't worry, we'll get there. Let's pretend that the Earth is two-dimensional and consists of three layers: outer space, our atmosphere, and the ground. And we'll use this model to explore how energy flows and feeds back to itself throughout this entire system. So let's start with the source of all energy, which is the sun. This is obviously not to scale, but the sun pours in energy from outer space down. Now, some of it goes into our atmosphere and is directly absorbed by the air in our atmosphere. But most of it goes down and just hits the ground. Now, our atmosphere is its own dynamic entity that can receive heat and give it, and it must stay in balance. And so what does our atmosphere do with its heat? Well, some of it sends up into space. And some of it, most of it actually, it sends back down into the ground. And lastly, the third component is the ground itself, which again receives heat and releases it. Some of that heat goes all the way up back into space and is lost forever. But again, most of it is sent back into the atmosphere. And this is where the greenhouse effect takes place. The more efficient this becomes, the better our atmosphere gets at absorbing the radiation leaving the ground, the more a warming cycle can take place, where it sets up a feedback loop where more heat is driven into the atmosphere and absorbed there and sent back into the ground and then sent back up into the atmosphere. A constant feedback loop that reinforces itself and generates warming in both the atmosphere and the ground. Now, like I said, this is a pretty simplified model, but this is the basic physics behind greenhouse warming. And in fact, without this greenhouse effect, the surface of the Earth would be much cooler than it is in real life. So we know this happens. And where the concern for climate change comes in is right here, by making this process too efficient. But actually following this process on the real complicated dynamic Earth is very intricate. So let me show you something else. To get a more accurate picture of what our climate is doing, and more importantly, what our climate will do in the future, we turn to computer simulations. These are fantastically complicated simulations involving physics, chemistry, biology, human activity models, is the whole deal. And they use some of the most powerful supercomputers in the world to try to understand at a high resolution, at great detail, what our climate will do in the future. And they have to include so many different effects, not just the basic physics of that greenhouse cycle that I just showed you. So for example, they need to model and account for our future greenhouse emissions with various targets or government agencies trying to reduce or ignore limits, like how much more carbon and methane will we dump into our atmosphere over the next few decades. They have to account for deforestation. Forests, land can act as a carbon sink, but then we cut down the trees and it's not that great of a sink anymore. And also, as we cut down the trees, we change what the land looks like. And this changes the reflectivity of the surface of the Earth, which changes the heat balance. We have to account for melting permafrost. There's gigatons of methane locked up in the permafrost of the tundra regions of our planet. And as those melt, the methane is released, which contributes to its own warming, and we have to account for that. We have to account for the role of water vapor in our atmosphere. And this is a very complicated cycle that depends on rainfall, cloud formation, even the size of raindrops and the amount of ocean circulation. This is fantastically complicated to model and understand. And we have to account for the loss of snow cover in Arctic regions or even annually in temperate latitudes. Again, this changes what the Earth's surface looks like, how reflective it is, how much radiation just bounces back off into space and doesn't affect our overall heat budget, and how much of it is absorbed and later retained and contributes to the greenhouse cycle. Plus that snow has to go somewhere and it becomes water vapor in the atmosphere, which again plays its own dynamic role. We have to account for melting of sea ice through the same thing. All these factors contribute to warming. But we also have to account for the factors that contribute to cooling. So for example, carbon sequestration policies. If we plant a bunch of trees or reduce our emissions or find other clever ways to eliminate carbon from the atmosphere, that will change the trajectory of our world. We've changed it already over the past 100 years. We can change it again over the next 100. We have to account for the role of aerosols in terms of building clouds or destroying clouds or changing the size of raindrops or just adding to the overall reflectivity of our atmosphere, where again, more radiation can bounce off into space and not be absorbed by the land in the atmosphere. And we have to account for ocean acidification. That is its own kind of carbon sequestration. It comes at great cost to marine life, but it is pulling carbon out of the atmosphere and altering the trajectory. And it's not just these effects, but how these effects and causes interact with each other and talk to each other and sometimes set up feedback loops. So for example, if you have ice in an Arctic region, that's very reflective and that sends a lot of radiation back up into space. But if some of it melts and exposes the land underneath, that heats it up, which contributes to warming, which contributes to more loss of ice, which contributes to more warming and more loss of ice, and it's a self-reinforcing feedback loop that simply doesn't stop. So all these computer models that we use try to incorporate all of these interconnected and sometimes self-reinforcing effects to try to predict what our climate will do over the next few years or even decades. That's why you might see a broad range in predictions from climate models, because different simulations, different teams, different researchers are playing with these different parameters, exploring how strong or weak some of these might be in relation to each other. And we have to fold that uncertainty in. But the simulations all agree that with the amount of carbon that we've already put in the atmosphere, the warming trend that we've observed will continue into the near future, even if we eliminated all carbon emissions starting today. To explore just how interconnected our climate system really is, let's talk to an expert.
So my name's Catalina, and I'm a master's student at Dalhousie University, and I study trace nutrient biogeochemistry.
That's exactly. A lot of prefixes. Can you walk us through those?
Prefixes. When we say biogeochemistry, what that really is the study of how biology in the ocean affects chemicals and the way that they move around the globe.
So you're examining these trace nutrients and how biology plays a role and then interacts with the climate systems of the Earth and the geology of the Earth to distribute them around the globe. What does that interaction look like?
You know, we call this planet Earth, but really it should be called ocean. When you ask people where most of the photosynthesis that happens on Earth is, they might respond to you that they think it's maybe a rainforest or something like that, but it's actually the ocean. Every breath that we take, every other breath, so 50% of the photosynthesis that happens in the world comes from the ocean. So you can say that every other breath that you take is made by these organisms called phytoplankton. In particular, we're really interested in the ones at the poles because out of that 50% of the photosynthesis that happens on Earth, a large portion of it happens at the north and south poles.
So there's a lot of photosynthesis happening in the polar regions, and then the polar regions, these are the regions most affected by climate change, right?
That's exactly right. And we've seen the biggest change in temperatures in the world changing at the poles, and that obviously has impacts for some of this primary productivity happening there. So just to take a step back, when I say primary productivity, that's production at the base of the food chain. So all of this goes on to fuel all of the other organisms that rely on this production, this carbon fixation that happens where organisms take carbon dioxide out of the atmosphere and store it in their cells.
What effects do those increased temperatures at the poles mean for microorganisms, for phytoplankton?
Yeah, that's an excellent question, and one that a lot of really intelligent people are working towards. So there are lots of different levels towards building that sort of knowledge to answer that question. And I think my research is really at the base of it. So what I do is I culture these cold adapted organisms, specifically diatoms. And so diatoms are a type of phytoplankton that have these really beautiful shells called frustules made out of silica. These guys are really cool because they are the powerhouses of that primary productivity that I've talked about. So we have these organisms that are really comfortable in the cold. And so what I do is I grow them in the lab. And since they're adapted to the cold, it takes a long time for them to grow. So anytime I do an experiment with these guys, it's a 3-month long thing. And it's like having kids. So
little tiny diatomic kids.
Yeah, exactly. And over the course of that 3 months, I might be in the lab every day, checking on them, giving them media, which is their food. And sometimes I expose them to high temperatures. We're really interested in how those high temperatures change the way that those organisms function.
So what kind of changes do you see?
Some of the things that we've found is that there are lots of different things, lots of different unexpected things happening when we involve both temperature and micronutrient limitation.
Okay, so the Earth is getting warmer, the poles get warmer, some microscopic diatoms get stressed out. So what? What's the consequence of that?
I'm kind of at the base of this research of understanding how these organisms work. And then the hope is that one day we can provide this information to people who build models. Some of the inputs to these models might be like, what is the community composition here? What is the temperature? What is happening with the micronutrients? And all of that stuff goes into a big mathematical black box, and they can model the way that those things work with each other and tell us about what the actual effect will be generally.
What would happen if, like, I flicked a switch and all the phytoplankton on Earth were to die?
Well, I think probably immediately nothing would happen, but very soon we would see a change in the composition of our atmosphere. And you can just contrast that question by, for example, what if all the trees went away? We would be missing out on a lot of oxygen.
And that'd be generally bad.
It would generally be bad.
Got it. So like in a worst case scenario, if we were to heat the poles too much, the diatoms wouldn't be able to survive because they're adapted to the cold. They would die. And so not only would we lose the source of all this energy, all this food, the diatoms also themselves act as a source of a sink of carbon. And so if they're not reproducing and doing their thing, then that just means even more carbon buildup in the atmosphere. And you have this nasty feedback cycle. Am I getting that right?
Absolutely, yeah. And so in terms of the short term, what we know about increasing temperatures and the way these guys are reacting, the magnitude of that temperature change is actually making them grow a little bit more.
Really?
So right now, they might be acting as the buffer against a lot of these changes that we're making to the atmosphere.
So what are some of the consequences of continued climate change? If we don't do anything about it, what are some of the effects of this?
We as humans, we borrow a lot of ideas about technology and engineering from life around us. Look at a helicopter. For example, we've learned a lot of things from very diverse groups of microbes, how to use biofilms in technology. There are many compounds out there that just haven't been discovered. And I think if we lose that biodiversity, we lose the opportunity to learn from life.
And so what do you see as the role of scientists when it comes to crafting policy and speaking to the public?
Some people just aren't great communicators. And so you really need those people who can be a direct connection between the public and scientists. I think it's really important as scientists to make the effort to write lay summaries for our papers, get connected in activism and talk to people about what we do. Make sure that when we talk about our science, it's not just a jumble of jargon.
That's very powerful work. Thank you so much for sharing it and for sharing your time with us.
Absolutely. Thank you so much for having me.
So what can we really do about this? Well, there are two main strategies. One is to reduce emissions, to find new manufacturing techniques and agricultural processes and modes of transportation so that we don't
pump out so much greenhouse gases into our atmosphere as we have over the past 100 years. We can also explore new technological ways to sequester that carbon, to pull the existing carbon out of the atmosphere by planting trees or developing new technologies. And we can also explore alternative energy. So much of our energy relies on burning fossil fuels, which is a major contributor to emissions of carbon dioxide. And the more we can lean on other sources of energy, the better off we'll be. And the other thing we can do is to prepare to mitigate the harm of climate change on human societies. So we can migrate vulnerable human populations to areas that are more stable or where they can continue agricultural practices. We might have to build a lot of seawalls to protect our largest cities. We might have to change our architectural practices so that we're more robust against hurricanes and tornadoes and fires. And we have to prepare for the damage that is going to come based on our past actions. But what to do about it, what to do about climate change, is a tough problem. And it's a problem that extends beyond the basic science. Climate science can tell us how the Earth got to be this warm. It can make predictions on how warm it will be. It can inform policy that if we make choice A versus choice B when it comes to emissions or sequestration, of what those impacts might be down the line. But it can't make the decision for us. The decision has to come from us, because climate change is something that affects all of us, so all of us have to participate in the solution. And navigating that is an incredibly tough job for climate scientists, for policy experts, and for you, for everyone. Is it too late? Well, the bad news is, in some sense, yeah, we've been doing damage for decades. We've been warming the planet for decades, and we're seeing the effects play out year after year. We're seeing the impact on agriculture. We're seeing the impacts of severe weather and rising sea levels. It's already here. The good news is it's not too late. It's not too late to change. It took 100 years of human activity to get to where we are now. And it might take another 100 years to reduce those impacts or to even potentially reverse them. But 100 years isn't infinity years. 100 years is 2 or 3 generations. We can do that. Humanity has the capability to enact change over the course of generations, to come to a consensus. We can not completely solve climate change in our generation, but we can take positive steps in that direction. And it really is just, honestly, one step at a time.